Natasha, Sergei, for inviting me to this wonderful place. And I want to try and link together a number of not obviously connected things. But I will say that this talk is really all about synchrony, about how objects, classical, quantum, biological, can synchronize, and about transitions between different kinds of synchrony, and to ask if there's any common problems. But I am driven originally by thinking about Bose condensation, and my view about Bose condensation is that you should think about it as the synchronization of oscillators. And I'll explain why, but I'll begin actually with a classical problem. And the classical problem is two oscillators. As you see here, two mechanical metronomes. And they've been set actually to the same speed, but because they're not completely perfect, even though they are German, you can just tell that they're just getting out of synchrony as time goes on, and if you can't see it, you can certainly hear it. Okay? And these are at the moment relatively weakly coupled. By the way, this is my own attempt at a kitchen table experiment. It is my kitchen table to do this. And so now I'm going to couple them, and I'm going to couple them together with a shoebox and two soda cans. And you see that this actually works really quite well. They've actually synchronized. I'd like you to now look closely about what's happening here, is that you see that they're synchronized, but they're sitting on something which is rocking backwards and forwards, and so it's inertially coupled. And it really is two nonlinear oscillators coupled via a large object, which is a cavity, which is going to mediate these. So later on, I will tell you that this is a polariton condensate, or at least after you quantize it, because to make this a polariton condensate, I actually need two quantum nonlinear oscillators, and that's an exciton, and maybe more than two, but I couldn't afford more metronomes. This actually does work with larger numbers of metronomes. And you need something that will couple them together, namely a cavity, and that will be an optical cavity. But this problem is a good place to start. Now, it's actually also a very old place to start, because this experiment was actually first done more than 300 years ago. And actually, I should test the students here. Who is this? Huygens, exactly, right. So, he was actually an expert in many things. One of the things he was expert in was clocks. And he was, I think, the second foreign fellow of the Royal Society. And this is the early 1660s for, I was brought up with British history, so I have to tell you that around this time, the monarchy had just been restored. The new king coming in, Charles II, discovered that these scientists were kind of useful, and so helped found an organization of sciences, the Royal Society. Okay, but the purpose of that was essentially military, and they gave out research grants, and Huygens had a research grant to make clocks, and the purpose of that was to construct clocks which would be very accurate, so that you could, of course, travel around the world and know exactly what longitude you were at because of the timing of the clock. And he discovered something, and it's sort of interesting to see how this discovery happened, by extraordinarily good research practice. So, firstly, if you're trying to build a very accurate clock, how do you know how accurate the time is? You can, of course, wait for 24 hours and hope that the sun would be up, but he was in Holland, and the sun is not actually up that regularly. So what he decided to do instead was to make two. And so he tried to make two clocks as identical as possible, knowing that they could not possibly be identical, and therefore he would be able to use the difference in time between the two as a judge of the error. Now, he was also a bit cheap about it, and therefore he built them in a common frame. So they were actually coupled together because they were in a big frame together, and there were two pendulums. And he discovered something that he reported, and this is an article to the Royal Society from this time, 1665. He discovered something which surprised him. Namely, check your Latin here, said consonorant semper reciprocationis, that they synchronized, okay? But that they synchronized out of phase. So rather than what I just showed you, if you like, the ferromagnetic alignment, his became antiferromagnetic. Now, he deduced, well, that they must be coupled somehow, and he deduced that the effect came from imperceptible movements of the common frame supporting the clocks. Nowadays we call these phonons, and you have two oscillators coupled and synchronized by phonons, and probably he would not have had much trouble understanding the BCS mechanism of phonon-driven superconductivity, right? Because he was already seeing this. Okay? A bit of history actually about this, which is, of course, the sad side. He sent this paper to the Royal Society, and it was read out loud amongst the members of the Royal Society, and it seems that they weren't impressed. Because they said, look, we're paying you a research grant to make clocks which are really accurate, and your clocks are so inaccurate that one clock can affect the time of another clock. This is not what we're paying you for, so it seems that the research grant was not renewed. Many of you will have had exactly this kind of problem. You discovered something that the agency didn't want to know about. Of course, mode locking is now the principle by which we tell very accurate time, but it took 3 centuries to get there. Okay? The other thing that they did, which was really annoying, is that they lost the paper. Right, so although this says 1665, it wasn't published until about 100 years later, when it was found in the basement of the Royal Society, along with a stack of other manuscripts that they had taken, but not published, right? So, of course, this is probably the first profound experiment in nonlinear dynamics, and the field was set back by a century by the poor filing mechanisms of the Royal Society. Okay. So, what do you need for this? You need a nonlinear oscillator. You need something which is driven, so we're going to get a non-equilibrium steady state by balancing between driving and dissipation. And we see actually that here there are periodic steady states that are stable to small external perturbations, but of course if the noise is too big there'll be a transition and they will decouple. Okay. But I want to focus for a moment actually on the difference between my experiment and Huygens' experiment. Namely, I got a ferromagnet and he got an antiferromagnet. And you say, well, okay, we think we understand why that is, and in fact one can model it very well. His was very largely elastic coupling. It's a very difficult experiment actually to get that experiment to actually work with elastic coupling. It's very, very difficult indeed. Inertial coupling is much easier. But you can imagine tuning parameters that would take you from one to the other. Okay? So maybe I could go from a ferromagnet to an antiferromagnet, or maybe you say, well, if I'm on the boundary between a ferromagnet and an antiferromagnet, like in a thermal system, if there's enough noise, if the temperature's high enough, I'll go via a disordered state, through a paramagnet, if you like. Okay? Or could you go through something else? Okay? And I want to tell you that the answer is something else. And I'll tell you the answer now, and then you can sleep for the rest of the talk. Okay. So actually what happens is you go through a state which is an intermediate state, which is actually chiral. And let me explain how that looks. So imagine I'm tuning parameters across here, some kind of coupling constant between the oscillators, and I'll be more specific about that. And there's a regime on this side where the oscillators are in phase, and there's a regime somewhere far away where the oscillators are completely out of phase. Some theorist tuning parameter. I'm going to tune a parameter in a model, and I'll show you that later. But I'm actually going to tune the non-reciprocity between these oscillators. Okay? So and first thing to notice is that at either end of these, there's a Goldstone mode. So when the oscillators are in phase or when the oscillators are completely out of phase, you don't know the origin of time, and therefore there is a U1 symmetry associated with rotating these. If you take snapshots of these things, they can be pointing, if you like, in any direction. Okay? And so there's a Goldstone mode which comes in here. Okay? Now, of course, if I've got an oscillator like this, say there's in pair, there's another oscillation mode which is pushing them away from the equilibrium position to the clapping mode. Right? So I can make something where even if they're in phase, I can perturb it and push them out of phase. And of course, that should be some mode which, if I'm stable, is massive, and therefore it will decay to zero. So I can look at the decay time, some kind of actually Lyapunov exponent, a growth rate. So here, on this side, there will be some damped mode which would bring the system back to equilibrium, but it should be massive. Okay. However, that can become unstable, and that massive mode can become degenerate with the Goldstone mode. Okay. By the way, notice that having two linear modes being degenerate is not legal if I have a symmetric or Hermitian system. The only way I can have two eigenmodes which are identical is to have a non-symmetric matrix. And there's a name for this special point. It's called an exceptional point. It's a point where this matrix is whatever matrix I'm going to use, the dynamical matrix, will be non-invertible. And so this damp mode can then become degenerate with this Goldstone mode. And at that point, then you say, well, there's some kind of instability in what happens. And actually what happens is that they begin to get a little bit out of phase. Just a small amount out of phase, but they chase each other. It's chiral. And so they will gradually run around in phase with this, and there's a frequency at which they go. Okay. And as you go further and further here, they get further out of phase, and the frequency gets larger, but then they get closer back in, and it comes back, and there's a second exceptional point. Okay. And this is sort of a generic way of making one transition from something which is a dynamical system from aligned to anti-aligned. And I'll basically be talking about this for the remainder of the talk. Okay. No, actually, unbeknownst to me, there were some experiments already, and these really are condensates. I'll tell you much more about this in a moment. These are actually two polariton condensates. So this is space, this is frequency. So what you think of this at the moment is a laser, a little micro laser which is sitting here, and another little micro laser which is sitting there. It's pumped, but they spontaneously condense. And you see here that they're actually, even though there are two of them, they're in fact coupled. There's a double well potential, and you can hop between them. And they're actually at identical frequencies, looking at these two peaks here. Okay. As you tune here, you're actually going into some disordered decoupled regime, where right and left are just different. But actually, if you notice what's happening here, in the middle, you can't see it so well on this, but if you look at this, you see that there's actually a big frequency come. Okay. Now, this is actually a difficult experiment to do. The way this experiment is done is it has to be done many, many times at a very high rate, and so you're seeing an average of all of this. But there's an interesting bit of frequency spectrum which is coming along in this aligned region. And I'll tell you a little bit more about this. So, the topics of the talk is, well, are there phase transitions between these? Of course, I just described something with two oscillators. We'd like to generalize that and think about something which in some sense has many oscillators. And can I make in a many oscillator system these different kinds of synchronized states? Does it have any analogies to what we're used to thinking about of thermodynamic phase transitions, if that happens? Are there in particular universal fluctuation dynamics that one could think about? Okay. And in particular, can you connect synchronized quantum systems like a laser and synchronization in classical models with this? And I'll try and give you answers to all of these. Okay, now, let me now turn to something vaguely quantum mechanical, although it won't stay quantum mechanical for very long, which is the idea of polaritons. Okay. Yeah, of course. Yeah, right.
So can you elaborate, so if I understand correctly, in the previous slide,
Sorry.
so here at the left side,
Right. Right.
you are elastic and then you are inertial.
Yeah. Well, yeah. So I mean, at least for this problem, and you can do it. So I showed you the inertial coupling limit where I had a rigid box, which was inertially coupling the two. Okay, right. Suppose I softened that box so that it could bounce up and down and not roll. Right. So the left-hand side would be I put those two pendulum on a soft support, which can go up and down, and it will still couple them, but it couples, in a different way than the inertial coupling that I get from having a rigid box.
So elastic, I understand that you don't exchange energy of the dissipation. Inertial,
Well, no, but I mean, with the inertial coupling, I mean, all of these things have dissipation, and you need to have driving. So notice that the oscillators, they're powered. They have to be able to go by themselves, right? Okay. So I think the inertial coupling is easier to see, really, because if there's low dissipation, then what happens is the center of mass stays roughly constant, so the box goes one way and the two others go the other, and it turns out that there's a stable mode associated with them beating backwards and forwards. Okay? Okay. The elastic limit is, in some sense, more heavily damped, and there's still a coupling, but the coupling occurs because when the oscillators move, they send phonons through the box, and those phonons can set up a periodic wave in the box, but the center of mass is essentially fixed. Okay. So now, by the way, if you're interested in this, somewhere back, there's this really lovely article, actually, on this problem, and subsequent to this, there have been some kind of nice scholarly articles analyzing the equations of this system, for which you need about 6, actually. So I basically need 6 first-order differential equations to do this, really 3 second-order differential equations, 1 for each of the pendula, 1 for the support. And the support is, obviously they're just damped oscillator equations, and you can couple them and you can analyze that. And there are many, by the way, there are many complicated states of this system that in principle you can find. Sometimes you can set up initial conditions where all of the energy goes into one pendulum and not into the others. So there's it's kind of rich, and I've really simplified it for the purposes of this. Yep, good. Okay, so let's quantize that system, okay? And so the cavity is now going to be an optical cavity, and so there are some waves confined to this cavity. And inside that cavity we'll have some two-level atoms, think excitons, but there are many ways of doing this. And then you can excite out of the ground state into an excited state, so I create an exciton here, and all of these other things are dull. But of course, if I can tune this excitation to be resonant with the excitation in the optical mode, I can couple them. Okay. Now, in fact, the systems I'm mostly going to show you, the cavities are actually two-dimensional, so they're basically like this tabletop. And so they're a flat thing, and the waves are confined inside this. And then I put some quantum wells in the middle, so there are lots of excitons that I can make in the middle. So I can look now at a dispersion of the modes, which is energy versus momentum, and momentum is the momentum in the plane. And And because I've confined it in one dimension, I take the light cone and I slice the light cone, and I generate a parabola for the photon dispersion. And the energy here is associated with having a half wavelength between the two edges of the cavity. This dispersion is very steep because, of course, this is asymptoting the wavelength of light. And then I have these excitations here, which in principle have some dispersion. This would be the mass of the exciton. But in practice, it's so very flat because we're dealing with wavelengths here which are going to be relatively short. Then, with some very good engineering, you can, of course, tune these things. And then in the vicinity of this point, if everything is coherent, they'll couple, and you'll get a polariton, which is a linear combination you can think of as an exciton and a photon. And because of hybridization, they will be split, and you'll generate these modes called polaritons. And this is the Rabi splitting between the two of them. And the lower polariton I can think of as being the in-phase mode. And the upper polariton I can actually think of as being an out-of-phase mode. Not of the excitons. The excitons are all in phase, but whether the excitons are in phase or out of phase with the optical association. Okay. So this is some dispersion curve. Then if you get creative, you can now start creating particles in this curve. Typically that's done by pumping either at very large energies up here and have things decay down, or occasionally you can parametrically drive by pumping with a laser on this cavity and creating states down here. And if you're lucky or clever, you can trap essentially bosonic quasiparticles down in the bottom of this potential. And if there are enough of them and the temperature is low enough, you might hope that you'll get a Bose-Einstein condensate. Then, if you do, then there'll be a distribution of states which will be very strongly peaked near the origin here. And you can actually measure that distribution relatively straightforwardly here, because I described the system as if it had perfect mirrors. It doesn't really. Some of the light will escape. But if the mirrors are flat, the light that escapes will keep the momentum that it had in the plane. So you'll actually see a peak in momentum distribution associated with light emission, associated with something kind of in the center here. And so you can actually map out this distribution. Okay. So, some numbers in general, one of the reasons that, so this can make high temperature condensates. This early experiment was done on gallium arsenide, so it's relatively cold, probably of the order of 10 Kelvin. But because you can get the mass here can be quite heavy, because it gains some of its mass from excitons. Of course, the collision cross-section can be quite big, because again, excitons can collide with each other. I'm sorry, and the mass is light, because the mass is sort of 50% photon. Okay? So if you remember that the Bose condensation temperature should vary inversely as some power of the mass, depending on the dimension, by having light mass particles, in principle, you can get high temperature conductors. And so now this has been done not just in gallium arsenide. Well, actually, the first experiment was not gallium arsenide. It was cadmium telluride. It's done in cadmium telluride and gallium arsenide, where you're dealing with regular semiconductors where it's relatively low temperatures. But much of this has been reproduced in many other systems, including organics, which have very strongly bound excitons. And lately, I'll show some data on tungsten diselenide in a cavity. And when you're working with those systems, you're talking about room temperature physics. Okay. Let me tell you how I think about this as a model. I'm going to treat excitons as spins, actually, because if I say that they can be empty or they can be singly occupied, but I'll forbid doubly occupied, then I can really label empty as down and filled as up. I flip the spins by exchanging a photon from here to there. Okay? So that produces a Hamiltonian, which is, I tend to call the Dickey model, but it's officially called the Jaynes-Tavis-Cummings model, that basically just has a photon in the cavity, an energy associated with the excitons, and there can be many of them, and then a coupling between the emission and raising of photons. And this Hamiltonian kind of nicely in the rotating wave approximation conserves the number of particles. The total number of particles, namely excitons plus photons, is conserved by this system. Of course, that's not completely true because there'll be things that will leak. But if I look at something like this, this actually, as you see, has a field which produces very long-range interactions between particles, and you sort of know what the ground state is. It's BCS. It should be a coherent state associated with a coherent state of photons and a coherent state of spins. And if you want to expand the spins out in Holstein-Primakov, this thing you could turn into pairs of fermions. And so this is really a BCS superconducting like wave function. So this is, so the ground state here is then a coherent state of oscillations of excitons and photons in phase. Now actually, by the way, there's another eigenstate of this where I change this sign to a minus. It's also an eigenstate of this in the mean field limit. Now, this is actually quite an old topic. It's been looked at for a long time, and all of the things that you would like to see with, let me call it generically BEC, you can see here's this distribution. If you look then at the modes, I drew these parabolas which were there in the presence of the just for the polaritons. When you're in this condensed state, you actually get a Bogoliubov spectrum. You get something which is linear here. So there's a sound mode which appears. You can, as I say, you can image the system and you can look inside and you can find vortices. Because it's 2D, you expect actually the transition is BKT-like, and that's been difficult to show because it's difficult to make systems which are very big to see phase fluctuations here. They're somehow there. There's some kind of there's some impurities in here, and actually you can create them over here with flow. So here you've actually created a condensate which is flowing. It's past a couple of defects here, so it's generating a vortex street, and you can go from fully superfluid phase. So this is a neutral superconductor, so there's no. But I say you can see things like BKT. You can also build condensates and couple them. Here are two, and so this is actually basically showing something like a Josephson effect. And now people know how to make arrays of these things with many thousands of condensates. And there's all kinds of games that people are playing with this, and it's actually very interesting and very exciting field. But I do want to talk now about something else, right? Although I should point out, by the way, that often there's a question about, if I go into a very dilute limit, does this really look like BEC? So here's some recent data from David Stokes' group. And so what you're seeing here are different populations, probably the temperature's roughly constant, and the fit is to a BEC-like curve. So it fits really quite well. And you can even do things where you're actually coupling together non-interacting objects like photons. So this is experiments from Martin Weitz's group in Bonn, a long time ago, where you have a cavity with dye in the cavity, and the job of the dye is to thermalize the photons to the temperature of the dye. And you can make things which are a photon condensate. I know in the textbooks it tells you can't make condensates out of photons, but actually you can. Of course, we've played with the population. Now, I want to get into the details of what this order parameter looks like microscopically, and I described it as, in terms of a condensate of polaritons sitting in the bottom level here. And that's certainly one way of looking at this. I mean, if you drive the system harder, you need a slightly more complex story, but this will do for a moment. And it's a steady state solution, but it's a two-component order parameter. The order parameter consists of light and matter. Now, you might say, well, why don't I make a condensate up here? This is, after all, non-equilibrium anyway. Suppose I could find a way of just populating the upper level. And that's also, presumably, if you can make it, a BEC in some kind of outer phase mode. But it's a different, physically it would look differently from this. It would come at a different energy. It corresponds to different two sets of things. But actually, in terms of what you would call a condensate, it doesn't have any different symmetry from if it was down there. Both of them have this U1 broken symmetry associated with a condensate, but they're just different internally. This is an internal degree of freedom, and there's no symmetry distinction. Okay. So you could imagine making, changing parameters somehow so that I make a transition between condensing here and condensing up there. This is not very far away from what we heard described by Gabriel Apley yesterday about, can you make things which, live in one mode or in another mode? This is just a different mode of the cavity. I can try and condense them in different ways depending on pumping them. But actually, as far as a condensate goes, they have exactly the same symmetry. So you can imagine that if I have two tuning parameters, and I show you do have them, typically pumping, how hard do I pump the system, what's the loss, you could imagine going from here to here there discontinuously, but because there's no symmetry change, you should be able to go around some point, which is down at the end of here, and that's a critical point. And it has a lot of analogies to a critical point in a liquid-gas phase transition, because there really is no physical difference between, well, there is a physical difference, but there's no difference in principle between a gas and a liquid. There's a huge difference in density. Okay? And so there should be kind of an interesting point where you go to look for phase transitions, fluctuation phenomena, and the like. Okay? Right. Now, it has to have a special character here because these are condensed modes. So when you look at this, it looks like a laser. It's emitting light at a very particular frequency. This is a different frequency. It's hard to imagine that you can have two frequencies inside the system coexisting, although it turns out that you can. But the simplest thing to imagine is that normally you go from one to the other and the frequency would jump. But if you go along a line, perhaps you can find a point where the frequencies actually merge together and they become exactly the same. And that will actually have to have this characteristics of a many-body exceptional point. It's a place where I have some dynamical matrix where two eigenvalues are identical. Okay. Now, yeah. Right. Well, no. To be honest, I don't actually know how they make this, but you can. It's more associated with exactly how you pump, right? So, by the way, we'd expect that there's hysteresis between these two, and I can show you some of that. But here's an example, actually, of a recent experiment from David Snokes' group, and this, as I say, is a tungsten diselenide monolayer cavity, and I forget the temperature of this, but this is high. This is not low temperature physics. So here you're looking at just them seeing the dispersion of the curve of these two modes, and you can measure it, and you see that somehow they found a way of populating the higher branch more than the lower branch. As you pump more, you get to a critical point where you get to threshold, but it's in this upper mode. So you can do that. The line width drops, the population grows. Very dramatically as you go through this. So this looks like some kind of lasing transition, really. Right. Another place one can see these things is often you have more than one threshold in the system, and so you pump. Here's a critical point where the condensate arises, and you keep pumping and pumping, and all of a sudden there's a new condensate which goes up here, and at that point there's a second threshold where the emission energy jumps. And you're going from, again, from one regime to another. There's some hysteresis around that, as you might expect. Okay? And as I said, Sometimes this is called a strong to weak coupling transition. Again, I'm not so much concerned about the microscopics. Here you're at very high powers. Here the system is beginning to look much more like a VCSEL, a laser. Down here the power density is much lower, so this really is a kind of a gas to liquid-like transition in that. But the point is that the normal phase to polariton or photon laser have the same symmetries broken, and so you don't need to have a transition. So how to describe that in terms of theory, just to be quick. Rather than doing microscopics, which one can, it's more natural to look at these systems in terms of some kind of coupled Gross-Pitaevsky equation. And so this is a nonlinear Schrödinger equation for a two-component field. Alpha is either light or excitons. The coupling between the light and the excitons is this Rabi coupling. You typically have loss in this channel. There's a minus I kappa, so this is the light frequency. There's some damping, there's some diffusion. And this is pumping, so you're adding particles into the excitons, and they will saturate at some level. Okay? No? And generically, I can play with parameters in here. Typically, the parameters you play with are kappa and p. And you can indeed find solutions where you have a double branch of this, one mode or another mode, and they come together and they merge at a point where the two are generic. So I'll call that an exceptional point. And notice that this is a nonlinear problem. This is not there's lots of work, by the way, done on exceptional points in essentially linear systems. Here the system, of course, has to self-tune. It has to find a solution of some nonlinear equation to do this. Now, what might that mean in terms of critical phenomena? So here's my view of a conventional critical point, where you imagine, again, this is, say, a U1 system, so there's a rotational symmetry associated with the order parameter, and there are naturally two modes, one which is the mode that goes around the Mexican hat, the Goldstone mode, and then a massive mode, which is always orthogonal to this in a system which is Hermitian. As you go closer to the critical point, this potential just gets flatter, and so this massive mode becomes very soft, but it's always perpendicular to the other mode. Here, what happens as you move in this space towards a critical exceptional point, the two modes merge. Everything turns into the Goldstone mode. There is no massive mode. The massive mode, if you try and push up the hill, everything gets kicked sideways and it runs around with this point. So this critical exceptional point is associated with, if you like, two Goldstone modes merging together, and so the fluctuations are expected to be much stronger, and they should show up in all kinds of ways. I don't think I'll talk about that because there's a little bit of experiment looking about this. Okay, so those equations were essentially classical. How am I doing? Oh, I think it's 9:40. Good. So when we saw this, I decided to walk down the hallway and talk to my colleague Vincenzo Vitelli, who's a soft and active matter expert, and we decided to see if there was an analogy in terms of well-known classical problems, and there is. But here I want to show you this with a bunch of robots. And we have blue robots and red robots. And the red robots like to align with each other. You see that they're pointing in the same direction. Similarly, the blue ones. But we give the blue and red robots conflicting instructions about whether to align with each other. And you can see what happens. So I say we give them, if you like, conflicting interactions. JB is equal to minus JBA. But blue likes to align with blue and red likes to align with red, so these interactions are all reciprocally coupled. Okay? And then you let the system go and see what happens. Okay? And there we go. Right. And you see that actually they started to rotate. We turned off the wheels, actually, so that they don't go around in circles, because we didn't have a big enough tabletop with this. But what you see is that it's developed a chiral state. It's actually so-called PT broken, this. And by the way, the symmetry is spontaneously broken. Sometimes it's right-handed, sometimes it's left-handed. You sort of don't actually know in advance. Another thing, by the way, is that if you do it with only 8 robots, it turns out that after a while, this will stop. If you wanted to get it to carry on forever, you need an infinite number of robots. So we didn't have a big enough grant for that, so we had to simulate. Okay. And so this is a model which is, I call hawks and doves. It's actually a version of those you know as a Vic-Sheck model, but there's blue and red, so think of these as birds flying around. The red birds like to align with the red, the blue birds like to align with the blue, and then the red and blue are conflicted. Okay. If you have a situation where the noise is big enough, nothing much happens, they fly around at random, here are their average velocities. If one interaction wins, they all fly together. If another interaction wins, they all fly opposite to each other. And then, again, in the model, you can tune parameters in between. And in between, you have this model, which is where now you can see that they're all flying around in circles. Okay? Now, you don't see spatial fluctuations here in this. That's largely because we produced a very large interaction length. So this is essentially described by mean field. Okay? So that comes back to this story I told you at the beginning, right? Is that I can think of anti-flocking, flocking, and in between, as I tune some parameter, which now I can be explicit about what it is, it's JAB plus JBA. Does one win over the others, right? And in the middle, you get this chiral phase with broken symmetry. You can look at that in a bit more detail, and it turns out that there are some other phases. So again, there are now 2 parameters in this model, and one way of thinking about this is that along this vertical axis here, as I have something which is perfectly reciprocal. So this is ferromagnet to paramagnet, sorry, antiferromagnet to paramagnet to ferromagnet. Nothing much interesting here at high noise. As you go to low noise, then you have a regime where there's aligned to anti-aligned. But at everywhere along this point, there's a gap in the middle which opens up, where you have this chiral phase. And the transition from the aligned to the chiral phase is always via a line of exceptional points. There are also other phases that you can find. After all, this is a dynamical system. It tends to do weird things. It can make time crystals. I'm not particularly interested in those here. Okay. It turns out that it's really quite general. Models with continuous symmetry, U1 or O2, and I'll show you later limit cycles do all the same thing. So contrarian Kuramoto models of this kind of thing, multi-component flocking. Also, interestingly, a well-known transition, Swift-Hohenberg, which is pattern formation, where there is, where basically this is space and this is time. So something is fingering and producing a pattern. There's a transition which goes to where the pattern becomes chiral. That transition, again, turns out to be an exceptional point. And you can actually generalize this to produce a phase transition boundary that looks really rather like this. Now, here, by the way, I'll say that I've divided things up into 2 classes of models. Models which are intrinsically PT symmetric, namely that the chiral phase is a spontaneously broken symmetry. So this is what I was just showing you. It turns out that models like polariton condensates, or for example a Kuramoto model, have really the analog of a magnetic field in them. And so there is some effective field which has broken the PT symmetry. And so that means you just have a slightly complicated, more complicated phase diagram, and there's boundaries emerging up here. And this is the coexistence region, an exceptional point that I just showed you from the original model. A little bit about space. Okay? This is back to the Vic-Sheck model. What happens if you look in the vicinity of some of these critical points and you begin to turn on gradient squared terms, spatial interactions? A lot depends a little bit on details of the model, and in particular for models like Vic-Sheck, which things are flying around, it turns out that always in the vicinity of these mean field-like critical points, you get some unstable states and formation of patterns. I'll come back to that a little bit later. I'd also like to point out that you can kind of generalize this to models which actually don't have any explicit symmetry, and in particular, a system which has something like a limit cycle. So what is a limit cycle? A limit cycle is when I have some solutions which produce an orbit, right? So it's a periodic orbit in a dynamical system, but the shape of that orbit isn't a circle or a sphere or anything like that. It can be some complicated shape. But the way you characterize those orbits is by basically taking a snapshot every period, and imagine you push a little bit away from that orbit and ask whether you flow back in or you flow away. So, of course, if you push along the orbit, there's a continuous symmetry around this orbit, so the rate at which you come back there is 0. It's a Lyapunov exponent, which is 0. And then if I have negative or positive Lyapunov exponents, I get things which are either unstable or stable. Okay. But you can now ask what happens in general when transitions where limit cycles try and merge. And these come in often sort of biological varieties. Predator-prey models are like this. So you've got predators and prey. Originally we had foxes and rabbits, and the journal was queasy, so we had to make the rabbits the predators, right? But again, these are very standard models, because what happens, of course, is that the predators are competing for the prey, and it's well known in predator-prey models that you can get oscillations, which naturally set up. Population of rabbits goes up, and they eat all the carrots, and then the rabbits die, and you get more carrots, right? And so they oscillate like this, right? But then there can be situations where the prey starts speciating and produce these oscillations where they can be out of phase, and so one predator beats another predator, and so there's an oscillation within the population. That is again described by a system which, when it has oscillations, there's always a 0 Lyapunov exponent, but there's a critical point where that Lyapunov exponent comes to 0, and that again is an exceptional point in this. And one that I'm fond of actually is of neurons. Sort of an ideal system to study non-reciprocal interactions are neurons, because neurons come in two kinds, basically, excitatory and inhibitory. An excitatory neuron makes the neuron that it is synapsing with more likely to fire, and an inhibitory neuron makes it less likely to fire. As a result, of course, of having a network of things like this, you can have spontaneous activity. We have to be grateful for this. But again, in models like this, you can go from in to out of phase delays as cycles come together. Okay, so then lastly, let me talk about what might happen beyond mean field. And to try and, so I already told you that you can just numerically find pattern-forming instabilities in these systems. It's hardly surprising for a nonlinear dynamical system that it does that. Sometimes these mask the exceptional points, but not entirely. And so just at the very end, as a theoretical exercise, I wanted to look at what happens when you go away from dynamical systems which are which have noise in them as an intrinsic part of their problem. And I'm going to take this flocking model, which you can think of as a non-reciprocal XY model. So again, I've got spins, The blue spins like to align with the other blue spins, the red spins like to align with the other red spins, but red and blue have different laws. And this is in one dimension. And so, in the absence of noise, if you like, temperature equals 0, I can find an axis along here where I go through a transition from a static phase to a chiral phase. So this is this exceptional point. And now I want to know what happens if I add noise. Because the systems are one dimension, you expect that the order is not going to be preserved anywhere. But it turns out to be quite different in two different regimes. So if I'm in a regime which looks like this static phase, where it really looks like an XY ferromagnet, it will disorder, according to conventional generation of domain walls, right? So that I can disorder the system quite smoothly, and I'll go to some regime which is disordered but effectively static. Okay. If I'm in the chiral phase, however, the chiral phase has a right-handed counterpart and a left-handed counterpart. And if you produce a fluctuation which turns a right-handed piece into a left-handed piece, you get a domain wall which has inherent dynamics. And those inherent dynamics then give you a very different form of the disordered phase. And these will cross over between the two. And the question is there some analogy to a so-called quantum phase transition? I say it's really an analogy. There's nothing quantum in this at all. Into a different kind of critical regime which covers all of those. Okay? So the way you look for that in a model like this is you look for measurement of some correlation functions. Because of course in a system like this, maybe I can just, whoops, wrong way. There are 2 degrees of freedom. There's phases for the red ones, there's phases for the blue ones. There's an average phase between the two, and there's a phase difference between the two. Right? Now, because if I have noise in some system, and just imagine that the average phases are locked, nonetheless, I expect at very long space or very long time, the system will roughen and it will grow disordered correlation functions. And the easiest way to measure that is to look for this correlation function, say to measure the order parameter at some time, average over some time x at different times t. Okay? So you would expect this to grow with some power law exponent. Okay? And you might expect to get a different answer if you're in the phase where these things are naturally rotating, because then you're switching as a domain wall between right and left-hand phase. So this is the correlation function that we're looking at. And let's start far away from the critical exceptional point. So this is a finite size scaling. So what you're looking at is you're looking at the correlation function scaled by the length to some power. So these are all different numerics from small systems to large systems. And then you can also look as a function of time along this, scaled again by the length with the exponent z. And far from the exceptional point, you get the answer that you would have expected. This is actually Edwards-Wilkinson scaling. By the way, the system does not allow KPZ scaling. That KPZ terms are forbidden. If you go closer to the exceptional point, the scaling of this order parameter, so this is divided by the noise, becomes much larger, right? So there's a real spike here, which is big. Okay, and if you measure just in the vicinity of here, you see a very different set of exponents. You see a z of order 1 and an alpha of 1.3 or so. And also what you notice is you're seeing kind of oscillations in here. And those oscillations are because that there's a sound mode in the system. And therefore, as the sound mode dies out, the mode which lives longest is the one which is exactly one wavelength inside the box. And that's why you see these oscillations, and that's also why, for this, in that sense, z is of order 1. Okay. there can be other stuff. Some of it is, decide whether interesting or not. There I didn't get any obvious patterns, but there are diffusion constants in this problem associated with the two components. Okay? And in the case where they're relatively similar, you get actually what's called a Turing-Hopf bifurcation. So you end up actually with a rather complicated but essentially periodic pattern, and you can turn it off by going here. In this case, if you put initial perturbation, it kind of dies out. So of course, there's a lot of richness in this. And one of the things which I find quite interesting about this is you look at this pattern and that it's periodic. There's noise done in these simulations. Okay? And so somehow the system has generated some kind of periodic order. And here you can see kind of interesting because the period doesn't quite fit in the box. So you actually get some complicated beating associated with that. So in this regime, interestingly, despite the fact that it's quite clearly highly disordered, if you look at this correlation function, instead of fitting to a power law, it actually fits to something which is quasi-long-range ordered. So this is fitting to log L, not L to some power. Even in the presence of noise. And so there's some kind of deterministic quasi-long-range order which is produced in ways that, frankly, I don't quite understand at the moment, and is sort of unexpected for 1D models. Okay, last comments. All of this talk has been very classical. I'm particularly interested in saying, can one go back to the quantum place, and is there a place where we could develop what I will call non-reciprocal quantum matter? There may be many ways of doing this, but let me just highlight two proposals, and these are not my work. Actually, these are from other groups. This is actually building a non-reciprocal Dicke model, which in principle one can do. So this is best done as a cold atom experiment, but I'm now going to have two species of atoms, but I can really think of them as being right-handed excitons and left-handed excitons. Those things you can make. Okay. They're coupled together again by cavity photons in a box, but there's a special way here by using a lambda-like transition to imprint on that box an extra phase. So I've got spins, I've got photons, but that I can go from, but I can add a phase, and I can continuously tune that as I go from one to the other. This is an interesting model because it has a kind of PT symmetry, in the sense that if I flip the population and I flip the phase, I get back to the same thing. It's less interesting in the sense that it seems to have exactly the phase diagram that the classical model does have. And I think that's partly because it's built in with long-range couplings. There's a more complicated story here, which is aimed a little bit at what one might be able to do with quantum systems. And to go back to this, sorry about the detail, but just think the Hubbard model. So you're used to the fact that in a localized model, the charge is localized, you just have a spin. I'm very nearly done, so this is good timing, thanks. The interaction between the spins is antiferromagnetic by super exchange. And that comes about because, of course, this electron can hop onto a doubly occupied site of a higher energy, but it can only do that if the spins are opponent. Okay? Okay. Now, you can interfere with this process by blocking this site. It's possible to imagine making an optical excitation which interferes with the process of hopping onto the site, but doesn't interfere with the process of hopping off. Right? And under certain ways of doing that, you can actually generate non-reciprocal terms. This is actually done for an RKKY model. So in the end, the dynamical equations would be Landau-Lifshitz-Gilbert. These are the standard ones. and you can engineer terms like this, and these terms in principle can get you ground states which look like the ones that I've been talking about, where, you know, where the spins actually go into some periodic rotation center from this. All theories for the moment. So here are my conclusions. There's, you know, I think, you know, a kind of a lot to do. It's sort of a, you know, sort of fun state, you know, beginning with this. And I should lastly, and I say it's easy to make in biology, how possible is it to do things like this in microscopic driven quantum systems? Of course, it's very hard because you want to get rid of heating and to be able to do things which are very specific to particular energy transitions. But there are ideas emerging. And lastly, I should thank the team that did all of the work, a couple of postdocs who are now safely ensconced in faculty positions in Japan and in France, quite a number of graduate students. Vincenzo Vitelli, my colleague who has been teaching me soft matter physics. And lately, by the way, we've expanded into trying to build real neural networks with real neurons. And so Stefan Ille comes from ETH Zurich and is plating cells in Petri dishes and looking for some of these transitions in real biological systems. And with that, I'll stop. Thank you very much.